All right, ladies and gentlemen, this is how to use a triple beam balance. A triple beam balance has to be tiered, which means you have to set it up so that when there's no weight on the pan, the two lines should meet here at 0. And if it doesn't, there's a dial you can use over here that's called the tare. And what happens in the tare is you turn it out or in, and it shifts the balance of the seesaw-like mechanism that the balance consists of. When you want to weigh something, once it's tared properly and it's calibrated to stay at 0 when there's no weight on the pan, what you do is you place the object you want to weigh on the pan, and then starting from the heaviest weight, you slide it to the first increment. You see that as soon as I put it to the first increment, the balance tipped the other way. So that means that 100 grams is too much. So we're going to put it back to 0, and make sure you always hook it carefully onto the notches that are cut into the beams, so that it's actually giving the weight that it says it's giving. The next one is to go to the medium-sized weight and keep on sliding until the balance deflects. Once it deflects, I'll move it back 1 notch. So 60 doesn't do it, 70 doesn't do it, 80 causes it to deflect. So that means it's less than 80, but more than 70. So I'm going to put it back to 70, and then I'm going to go to the smallest weight and slide it until the balance actually balances at that line. So when those two lines line up like this, we know that we've got it at the exact weight. So I'm going to slide it back a little bit. And what we get, and then the way you read the weight is by looking at the beams. So once it lines up, read the weight by starting from the biggest increment, the biggest weight that was used. So in this case, the medium-sized weight was used. It's at 70, and then the smaller weight is at 73, and then you count 8 lines in, so it's 73.8, and then it's in between the line for 8 and 9, so we're going to estimate it's around 8.2 or 8.1. So I'm going to say this is 73.81 for the weight of the copper block. Let's see what my class got. For copper, they got 72.63. So I got 73.81. They got 72.63. That's well within experimental error. And as it turns out, there's more than one copper block, so it's possible that I got a different block there. The density that we got when we measured also the length of the block, which is 19 millimeters, which turns out to be 1.9 centimeters, allowing us to calculate a volume of 7.6. I put liters cubed there. I meant L cubed as in length cubed. So the units, don't be misled by the fact that I put L cubed there. What I meant in units was centimeters cubed. And the volume is always 7.6 because all the blocks are the same size. And the density we got for copper turned out to be 9.56. And when we looked up the literature value on this periodic table, it came comparatively close. The actual literature value is 8.96 grams per centimeter cubed. So it's not exactly what the literature says, but it's well within acceptable experimental error, and it was a learning experience in that regard.